started. To quickly recap where we were last time. Right? We spent the last lecture talking largely about this idea of a boundary layer and how we can have two different types of boundary layers that we're really going to be concentrating on in this course, those being the velocity boundary layer and the thermal boundary layer. So if you have some surface, right, we'll call this a solid surface, and we'll assume that it is at some uniform temperature, which will denote T sub S, right, for surface, and we have some fluid, usually, air, water, oil, something that can behave as a Newtonian fluid that flows past the surface. We'll say that that flow has a velocity of u infinity and a temperature of T infinity. And the idea is we have between this free stream, as we would call these quantities with the infinity subscripts, and the quantities at the surface, we end up with this small region of flow where the velocity goes between this non-slip condition at the surface, right, where u is equal to 0, and transitions from that to this uniform free stream velocity of u infinity. And so we would call this layer where the velocity is transitioning the boundary layer, and we denote that thickness of that layer by the sign delta. At the same time, we have a thermal boundary layer which does not have to be the same thickness. So we could draw a separate region here where if we were to plot the temperature as a function of y, we would see that the temperature transitions from the temperature at the surface to this free stream temperature. Inside of that boundary layer and outside of the boundary layer, it's uniform. So this thickness of this thermal boundary layer we call delta T, where that T subscript tells us that we're talking about the thermal quantities. So the important takeaway, right, is that the boundary layer exists as a thin region, right? Usually these deltas and delta T's are very small, a very thin region of flow between the free stream and a surface where shear stress, diffusion, right, these become important. And so, especially when we're talking about convection, right, which we said is really a combination of two things, conduction and advection, that is spreading or diffusion, and that whisking along of energetic particles by the flow, it's in this small region that we really start to get that balance between the diffusive behavior and the advective behavior. So, inside of this boundary layer, we said, right, for convection to occur, if thermal energy is going to leave this solid surface, right, conduction carries it up to the surface, and then in this tiny, infinitesimally thin layer of fluid that is stuck to the surface by this non-slip condition, it has to cross that thin layer by conduction as well. So we ended up with an energy balance that said it gets into the fluid by conduction, and from there, that advection starts to take over. And previously, we used that result to develop an expression for our convective heat transfer coefficient H, which went as follows. H equals negative K sub F, so this is the thermal conductivity of the fluid, times the temperature gradient evaluated at y equals 0, that is at the wall, divided by the temperature jump between the surface and the exterior fluid. So this here led to a couple of conclusions that I want to reiterate. First, right, we said that delta and delta T, well, this isn't really a conclusion. This is leading to one of these conclusions. Both delta and delta T tend to increase as the flow progresses along a surface. Okay. So boundary layers grow thicker as they move along an object. Increase as x increases. As a result, this temperature gradient, dt, dy, tends to decrease as x decreases. And following from that, we found that h tends to decrease as x decreases. So this tells us, as I said, a couple of important things. First, h is not a constant. Okay, up to this point, right, in chapters 1 through 5, anytime we used convection, we were just given a number for h. And that number was just a constant, right? 25 watts per meter squared Kelvin. Right? That is kind of an oversimplification of the reality of things. What we see is that the efficiency of convection tends to get diminished by the growth of this thermal boundary layer. So, takeaway number 1, h is not a constant. Okay, we would define h as being some function of x and y. So in general, it's a function of the space or the position on a surface. And so if we want to define q double prime n, that is the heat flux out of a surface or into a surface, that would also be a function of space, right? X, y. And we would define this as h ts minus t infinity, right? Where h is allowed to vary. And because h is not constant, and therefore q double prime n is not a constant, if we want to figure out the total heat rate, we have to break out that integral that we've been trying really hard to avoid since chapter 1. So if we want to write the total heat flux out of a surface, this becomes an integral over the surface area of q double prime n, which works out to t infinity h dA. Or if we define this mean convection coefficient h bar, we can write it in a friendlier way. So it's the last little bit of review here, right? This h bar, so as I said, this is the average convection coefficient. So if it varies, if h locally varies as a function of your position on a surface, if you take the average across that entire surface, h bar equals 1 over a, the integral over a of h dA, right? The classic definition of how you take an average of something over an area. Then we can just pull it outside of the integral. And if we assume, right, as we did before, that the surface temperature is uniform and that the free stream temperature is uniform, then we can calculate on the basis of this averaged convection coefficient what the net heat rate out is in watts. Okay. So that's conclusion number 1. H is not a constant, but we can treat it as a constant if we go through this process of averaging it first, only to find the net heat flux out, or heat rate out. Conclusion number 2 is, if we look at, right, this equation right here, this tells us that if we know something about our fluid properties, namely the conductivity, if we know what our surface and our free stream temperatures are, and if we actually have a profile of what our temperature distribution is in the boundary layer, then we can actually find the local heat flux directly. So for example, if you have a plate, right, flow past a plate, and you were to put a temperature probe into that and measure the temperature profile across that boundary layer, you can use that information to back out a convective heat transfer coefficient directly. So we're going to illustrate this through an example. So if t is a function of y is known, h can be found directly. So, as an example, let's consider a case where we have airflow. okay, occurring past a flat plate, as I just said. So here's our plate. We have airflow occurring past it, and temperature measurements have been obtained experimentally that tell us that the temperature distribution, the non-dimensional temperature distribution, follows this expression here. 1 minus e to the negative Prandtl. Okay, so there are some expressions here that we haven't seen yet. This PR is what's known as the Prandtl number. We'll be getting into that in a couple of lectures. And then over here on the left-hand side, right, the temperature has been normalized by subtracting the surface temperature and dividing it by the total temperature jump. Okay, but the idea is we could just reorganize the equation here to write it for T directly, so that that number you would get at the end of your temperature probe would be that T. So we're given the following information about this airflow. The free stream temperature is 400 Kelvin. The surface temperature is 300 Kelvin. This U over nu, right, the ratio of the free stream velocity to the viscosity, is 5,000 1 over meter. And this Prandtl number, which we don't need to worry about yet, just has a value of 0.7. Okay, so what we're asked to find now is if this temperature distribution, right, is defined at some position x from the leading edge of the plate, we want to find what the heat flux out of the plate is at that position. So we're seeking to find Q double prime N at the same x location as we've obtained this temperature distribution. Well, the first thing we need to do is write out the equation that we're going to be hammering away at. So I'll rewrite it here to avoid scrolling up. We're going to recall that equation we just had written down that said Q double prime N, H is equal to negative K F dt y evaluated at y equals 0 at Ts minus T infinity. Okay, this is one way we could approach it. If we wanted to, we could evaluate this dt dy at y equals 0, multiply it by this conductivity, divide it by this, get our h, and then multiply it by this again, right? But what this is really telling us is if we were to take this T sub s minus T infinity and multiply both sides by that, we end up with a more useful version of the equation. It says h times Ts minus T infinity is equal to negative Kf T y at y equals 0, right? And both of these quantities are actually equal to this Q double prime N that we're looking for, right? So this is just an expression of the surface energy balance. Convective heat flux, right? This is Newton's law of cooling. Conductive heat flux, right? This is Fourier's law, and they are both equal to the amount of thermal energy per unit area flowing through the surface. Pretty straightforward. So we're going to take advantage of the second one of those expressions, right? That negative Kf times the temperature gradient at y equals 0. We're given the temperature distribution, right? So it's easy to take the gradient of that. We're given, or we can find the thermal conductivity of the fluid because we know that it's air and we know that it's at 400 Kelvin. And we can just plug those numbers in at y equals 0 to get the result that we're looking for. So we'll just zip through this a little bit. if we turn to table, I believe it's A4 in the back of the book, we would find table A4 tells us that air at 400 Kelvin has a Kf value of 0.0263 watts per meter Kelvin. Okay. And we could write our temperature gradient from, let me zoom out a little bit so you guys can see. We could use this equation right here for our temperature distribution to figure out the temperature gradient. So that would be a matter of just multiplying both sides by that T infinity minus T sub s, and then taking the derivative with respect to y of both sides. And what that would give us is T infinity minus T sub s times Prandtl u infinity over times negative Prandtl infinity u. And we should have nope, that's right. Okay, and so now that we have this, if we evaluate it at we plug in negative K sub f times the temperature gradient at y equals 0, we would end up with, right, here's our K sub f right here. So 0.0263 watts per meter Kelvin times, evaluating this temperature gradient at y equals 0 just means plugging in a 0 into the y right here, which turns that exponent into a 1. So this becomes 400, oh, this should have a negative sign in front of it. There we go. 400 Kelvin minus 300 Kelvin. Right, there's our T infinity minus T sub s times that Prandtl number of 0.7 times the ratio of U infinity to nu, which was given as 5,000 meters negative 1. And what this all boils down to, if we plug it into a calculator, is negative 9205 watts per meter squared. Now that we have, right, that 9205 watts per meter squared, we know that that's the total heat rate or heat flux. So that's a useful quantity for us. But let's, right, what we talked about was backing out that convective heat transfer coefficient H. So let's take advantage now of the fact that we know this quantity. We got this quantity from this quantity, so let's find this quantity from that result. Okay, so we're plugging in that solution into Newton's law of cooling to say that H is equal to, right, Q double prime N divided by T S minus T infinity, which is 9205 watts per meter squared divided by 300 Kelvin minus 400 Kelvin, right? And this is going to give us a value in the end of 9205 over 100. So 92.05 watts per meter squared Kelvin. So what we did there was we said, right, here's a hypothetical situation where we've measured the temperature profile in the boundary layer. We've resolved that. We have that knowledge, and we can use it to calculate almost everything else. Okay, we figured out the total heat rate or heat flux at Q double prime, which is something of engineering interest. If we were to measure that temperature profile at different points along that plate, we could integrate that resulting heat flux along the length of the plate to find the total heat rate in watts. If we want to figure out H, we can get that from the results. And if we figured out H at different points along the plate, again, we could average that and come up with the averaged convection coefficient. So this is an illustration of how useful it can be to know the temperature distribution and leverage that to figure out these results that are of engineering interest. The problem is we don't, in general, know what the temperature distribution on or across a boundary layer is going to be. This is a really hard result to get experimentally, and it's something that, in general, we can't get just through theory. And that's an idea that we'll be developing in the next couple of lectures. So there's a little more time than I expected to spend on the recap, but I want to talk about sort of my goal for the next couple of lectures. Topics for today, and we'll probably spill over into Wednesday. I want to discuss the governing equations for boundary layer flows, that is, the equations that govern the fluid motion and the temperature distributions in a fluid flowing past a surface. So, governing equations for, both for velocity and temperature. And I want to discuss boundary layer types, that is, laminar versus turbulent, and what that means to us in heat transfer. So I'm going to do a little bit of switching around right here just to better manage the time. The governing equations is going to be sort of a long theoretical lecture. Okay, so we're going to break that up and talk about these boundary layer types first. So, we've covered the idea of what a boundary layer is. And in fluids, you should have at least some inkling, of what kind of forms a boundary layer can take, the difference between laminar and turbulent boundary layers. So this should be a review, or for those of you that slept through that fluids lecture, this will be a primer, on boundary layer theory. So laminar versus turbulent boundary layers and why it matters. So the idea is flow past some solid object. Again, we'll leave this as a flat plate because it's the easiest to work with. If we characterize the upstream flow as having a uniform velocity profile, u infinity, then the boundary layer will begin at the upstream edge of this plate. So we'll end up with this region of velocity variation. We'll call the edge of this boundary layer, we'll denote it by this green line. And as the flow progresses along the plate, at some point, our fluid streamlines are going to go from these nice, straight, organized sort of lamina, as they're called. They're going to start to develop these instabilities and waves in them, and eventually devolve into this chaotic, roiling, turbulent motion, which is where the turbulence gets its name. And when that happens, the boundary layer thickness goes through this jump. So turbulence is characterized by two things: chaotic motion in the boundary layer and a thickening of the boundary layer. So we would say that upstream of this we have laminar flow, which is well organized. Downstream here we have turbulent flow, which is characterized by chaotic or fluctuating velocities. And between these 2 points, we'll go ahead and draw this with a little red, arrow here, right? Between these 2 points, we would say this is known as transitional flow. So a couple characteristics of each flow regime. Laminar streamlines are typically parallel. Okay, they don't tend to cross one another or mix. And so, right, the spreading out of energy, it tends to be accomplished through diffusion primarily. So as a result, this is less efficient at transferring thermal energy. Turbulent boundary layers are characterized by large-scale mixing. Right? If you take a look at this, right, the idea is we're developing all of these eddies and these roiling flows, which do an excellent job of spreading things through the boundary layer. One of those things being thermal energy. Very efficient at transferring thermal energy. So as a consequence, right, of these differences between the laminar and turbulent boundary layer, obviously it's the second bullet point that we are most interested in heat transfer. We could draw sort of a schematic of what this convective heat transfer coefficient H looks like inside of a boundary layer. So we X here, where X is the distance along the plate, and here we H. What we would find is in the laminar boundary layer, right, we start out with some H up here. What did we say happens to H as you progress along the distance of a plate? Forget about this jump between laminar and turbulent. For boundary layer, we said H is going to, what, increase, decrease? Right. It's going to decrease generally with some sort of power law behavior. Okay. When you hit this region of transitional flow, it's going to tend to spike upward, and then inside of the turbulent boundary layer, it's also going to decrease, but that enhanced large-scale mixing means that it remains higher than it was in the laminar flow. So you have this sort of piecewise behavior where, right, it decreases within each type of boundary layer. But when you jump from one type to the other, it goes through this huge increase. So we'd say this is laminar, this is turbulent, and here's our transitional region. So it's important to understand this because, right, when you see engineered products that rely on heat transfer, or rely on convection as a mode of heat transfer. Think heat sinks on electronics or motors. Designers tend to try to maximize the amount of turbulence that, of the flow over those surfaces. The idea being that just by creating some turbulence, right, by putting some bumps on the surface or creating some sort of geometric features that create this sort of eddying flow, they make those surfaces much, much more efficient at getting heat away through the action of convection. So let's illustrate this with another example. Consider we're gonna be doing a lot of flat plate problems. Just so you're forewarned. This is another one. Consider, right, flow past a flat plate. This time we're dealing with water. So we have water flowing past a flat plate with a free stream velocity of 1 meter per second. This flat plate has a length of 0.6 meters. And experiments have shown the following. that the convective heat transfer coefficient H can be written as a function of X, and it tends to follow one of two behaviors. It can be described as a C sub L coefficient times X raised to the negative 0.5 power in laminar flow, and C sub T times X raised to the negative 0.2 in turbulent flow. Okay, so right, this here indicates that some poor lab tech would have to go through different positions of X along the plate and take the temperature profiles and use those temperature profiles to back out H like we did in the previous example, right? By doing it at a bunch of points and then fitting that value of H to a value of X within each type of boundary layer. Additionally, it's been determined that at a temperature of 300 Kelvin, C sub L, right, our laminar coefficient, is equal to 395 watts per meter to the 1.5 Kelvin. Right, this weird power on meters is because we have a weird power on X out here, so that the product of those two will give us that watts per meter squared Kelvin that we're looking for. C sub T is equal to 2330 watts per meter, this one to the 1.8 Kelvin. And the viscosity, right, the kinematic viscosity nu, oh, come on, there we go, which is equal to dynamic viscosity over density, is 1 times 10 to the negative 6th meters squared per second, approximately. So those of you that are doing the reading, you might recognize this as being a modified version of example 6.4 from the book. So if you want some extra details on this after the lecture, you can look at example 6.4. Okay, so what we're asked to find is H bar. Okay, not just H. We're given H as a function of X for each of these two regimes, but we're asked to find H bar, the averaged convection coefficient. So this seems pretty straightforward. We did a example a lot like this on Friday's lecture, right, where we were given a function for H, and we went ahead and evaluated that integral to figure out what the average was. The difference here is that we've got to jump between two different types of H, and we're going to have to figure out where that jump occurs. So this brings up the idea of, I'm going to add it as an aside here. The critical distance and critical Reynolds number. My eraser has decided to quit on me. All right. So some of you might remember from fluids, right, that when we're talking about the difference between laminar and turbulent boundary layers, that distinction, okay, you can see the difference, but when does that difference occur quantitatively? Right, what sort of variable do we use to describe the behavior of boundary layers? The answer is the Reynolds number. That is the governing parameter that dictates what a boundary layer is going to look like, how thick it is, what sort of shear stresses develop in it, right? And so, in general, we'd say that a boundary layer transitions that transition between laminar to turbulent flow occurs approximately such that the Reynolds number is equal to U infinity times x over nu is around 5 times 10 to the 5th. So for most flows, right, U infinity is going to be a constant, nu is going to be approximately constant, and so what this is a linear function of the distance along an object. So for our flat plate here, right, x would be measured from the upstream edge, and we would say that that jump from laminar to turbulent occurs when this quantity, right, at some x such that that quantity equals 500,000. So what we're going to do first is figure out where that jump occurs on this plate, and then we're going to see how we would use that to work out the net average convection coefficient across the plate. So step 1 in the solution here is going to be find the transition point x sub c, called xc or x critical. So we're looking for Reynolds number c equals xc infinity over nu equals 5 times 10 to the 5th. If we solve this for x sub c, we get Reynolds number, or, well, 5 times 10 to the 5th times nu over u infinity, right? Which for this case works out to 5 times 10 to the 5th times 1 times 10 to the negative 6th meters squared per second, right? There's our value of nu, and 1 meter per second, which is our free stream velocity. So this is pretty easy to evaluate just because everything's either a 1 or a 5. We can cancel out some powers. And what this tells us then is that x sub c is equal to 0.5 meters. Okay, so we set up that criteria on the Reynolds number and just solve for the distance along the plate at which the flow will meet that criteria. Step number 2 is going to be to break up our integral for the average convection coefficient. So break up integral. So h bar, right, for this case is going to be written as 1 over the length of the plate times the integral over the length of the plate, the L of h x dx, right? The issue is that h goes through the significant jump somewhere in the middle at about 0.5 meters. So we could write this instead as a piecewise integral, where it's 1 over L of integral from 0 to that critical point where it jumps of h laminar dx plus the integral from x sub c to the end of the plate of h turbulent dx. Everyone see what we're doing here? I'd like to see a show of hands if you're with me this far in the process. Okay, that's good. So we have those expressions for H laminar and H turbulent, right? I've added these laminar and turbulent subscripts so it's clear which ones we're talking about. But we have, right, for H laminar, we have that CL times x to the negative 0.5. And for H turbulent, we have CT times x to the negative 0.2. So at this point, we're given CL and CT, so we have numbers for those. We figured out what x sub c is up there, so we have numbers for that. And L is that 0.6 meter length of the plate. So everything that was previously in symbolic form, we have numbers that we can use to crunch. So going through and evaluating these integrals now, we're going to go ahead and do it symbolically first and then plug in the numbers at the very end. We would say this is 1 over L. This first integral evaluates to be CL over 0.5 x to the 0.5 from 0 to x sub c plus CT over 0.8 x to the 0.8 from x sub c to L. And so now, plugging in those numbers, we get, this is 1 over 0.6 meters, 395 watts per meter, 1.5 Kelvin over 0.5 times 0.5 meters to the 0.5. All right, so there's our first term, plus 2330 watts per meter to the 1.8 power Kelvin over 0.8 times 0.6 meters to 0.8 power minus 0.5 meters to the 0.8 power. So if we broke out our calculators and evaluated this, we'd find that H bar is equal to 1368 watts per meter squared. So what's nice about this, right, is we've taken a flow that actually involves a laminar boundary layer, a turbulent boundary layer, and a local heat transfer coefficient or a convection coefficient that varies as a function of distance in each of those boundary layers. So we're dealing with a problem that involves a lot of the complexity that we're saying can exist. Okay? And we boiled it down to a version of the heat transfer or convection coefficient that's amenable to Newton's law of cooling in a way that we've been using it so far. So if we wanted to figure out, right, Q, not just the heat flux, but the heat rate, right, in watts, we could say that Qn is equal to this H bar times some temperature difference, Ts minus T infinity, times the area of that plate. And we're done. All right, so there's a lot of things to be said for this going through the trouble of coming up with an average heat transfer coefficient, because it makes a lot of the ensuing calculations easier, especially when you're interested in finding what the power transferred through a surface is by convection. Yeah? Huh? I did. I forgot a Kelvin there. Thank you. And I also just quickly wanted to reiterate that, right, we were given these two expressions for the values of H in each of our flow regimes, right? One for laminar, one for turbulent. As I did before, right, I sketched it before, but if we were actually to plot out these two H functions, we would see again that what we've done is X, H. We have essentially, we're given one that describes turbulent or laminar flow, and another that describes turbulent flow. Okay, and so what we did here is we said, based on the velocity of the flow, we figured out what x transition occurs at, and we said, fine, we're going to integrate over, let me make this larger. Said we're going to follow the laminar behavior up to that transition point, and then we're going to jump up to the turbulent behavior. So we created our piecewise function out of two functions that dictate the flow, or the heat transfer behavior in each of those two flow regimes. If, let's say, if, hypothetically, we were to heat the water, or not heat the water, yeah, we could heat the water up. Let's say we heat the water up a little bit. Let's assume that our CL and our CT remain the same, so that these red and blue curves are not changed. All right. If we heat the water up, the viscosity would decrease. the viscosity decreased, our Reynolds number at a fixed position in space would tend to increase, meaning that transition would occur earlier or later. Any takers? Earlier. I heard that somewhere. It would occur earlier, right? So we would make this jump, not at this position, but somewhere upstream of that. Okay? Which means we've done away with some of this region of small heat transfer coefficient and replaced it with a greater heat transfer coefficient of the same area. So our averaged H, right, our convection coefficient over the entire surface would actually increase. So this is should be an indication of how we could manipulate the boundary layer a little bit in order to control what our convection coefficient does across the plate. Okay, so this is definitely going to have to wait until Wednesday. The next thing we're going to be talking about is going to be the boundary layer equations, or rather the governing equations for the fluid and the temperature. So I'm just going to preface this a little bit by saying we're not going to be deriving these from scratch. You did that in fluids. You'll do it again in intermediate heat transfer. But what we are going to be doing is restating them and talking a little bit about the physical significance of each term. So without writing the equations themselves, the one thing we can say at this point, hopefully everyone's on board with, is thermofluids in general, right? Heat transfer and fluids. The equations have to obey a set of universal physical laws, right? So these are the way we built up these equations in fluids, and we're going to go ahead and review them now. The first is conservation of mass, right? The idea that mass is not going to be created or destroyed. In fluids, this led to this thing that was called the continuity equation. And in heat transfer, or rather in this class, heat and mass transfer, there's a second sort of variant on this that we would call the species equation. We'll talk a little bit about this. This has to do with the mixing of two different concentrations of matter in a fluid, but this is not going to be a focus of the class, right? This is something you're going to save for later on. So that's number one, conservation of mass. Number two is Newton's second law, which is more familiar to you as F equals ma, right? So in fluids, right, we chose to recast this in the more general form. We said F is equal to the time rate of change of mv, and we turned this then into the set of equations we called the Navier-Stokes equations, which I know were your favorites. The third fundamental physical principle that all these flows have to obey is going to be conservation of energy, or the first law of thermo. Right? And so the way we've been doing this so far has been through our energy balance. E dot, so the rate of change of stored energy, just want to draw a dot, is equal to the net rate of energy in minus the net rate of energy out, but plus so rather the net rate of stored thermal plus mechanical energy is equal to the difference between the thermal and mechanical energy in and out plus the net rate of conversion of non-thermal, non-mechanical energy into one of those two. Okay, so something like chemical reactions, nuclear heating, electrical heating, etc. So I'm going to leave you to stew on these a little bit for the next 2 days. We'll come back and we're going to discuss these in greater detail on Wednesday. Have a good day, everyone.